Well, welcome back everyone so far. We're just going to run the clock and get started in just a few moments. Almost there. The promise is if you come in right at 2 o'clock, you'll never have missed anything. And it looks like we can start. Welcome back everyone. So today's class is going to be a pretty exciting one in my opinion. We're still dealing with the definition of the derivative. Section 3.2 could have really been combined with 3.1. We're just looking at extra conceptual questions. And we're taking another look at the definition of the derivative. So we'll calculate this as well when we're in the notes. Then we're going to be changing gears. It's important to know the definition of the derivative. It's through a limit. But if you use that definition of the derivative, we can find a whole class of functions, whether they're polynomials, exponential functions, and otherwise, for which we can take the derivative without resorting to the limit definition each and every time. So section 3.3 is where we kind of get to a fun part of the course where derivatives are going to be calculated a lot faster, a lot less algebra. Below, I have some review materials. These are from earlier up in the notes, but I just moved them down to this part of the Moodle page because we'll be doing a lot of stuff with exponents. So you might want to brush up here if you feel like you're a little bit rusty on exponents. Also, last thing here is that we have our new quiz. I posted this on the prior week, but then on last Wednesday, I felt like we didn't get far enough for that quiz to be well supported. So I moved it down to this week here and moved down the due date to October 2nd. This quiz is about calculating the derivative by using the definition. And we really have to use the definition here to get full credit on that kind of problem. So this will be a quiz problem, quiz 3. It'll also be a problem you'll see on the exam 2 as well, a potential final exam question as well. I think that's all my announcement so far, folks. Any questions or comments before we get started today? Okay, so let's get going. Oh, before I get too far ahead, I did have one announcement that I had to put out there this morning. It's always unfortunate to have to do these things, but I have another meeting today with the math department, and this is the one that happens on September 25th. It's going to intersect with the office hours, so I won't have office hours today. But if you do have questions after class, don't hesitate to write an email. I'll be very happy to get back to those emails and answer each and every one of them. So I have an interruption on office hours today, another one on October 16th, and the final one on November 6th. Sorry about those. That's always kind of inconvenient for really everybody. Well, aside from that, oh, didn't mean to leave the Moodle course. This is where we left off in section 3.2 last class. We're on example 3, and we're just taking another look at the definition of the derivative f. What I have highlighted here is we're mostly focusing on the geometric nature of the derivative. So no matter what, every time you see f prime of x, or if you see instead of f prime of x, if you see in Leibniz notation, dy dx or df dx, all of these things are a slope. So that's what it's saying in yellow. If that limit here exists, then the value of that limit, which we call f prime at x, the derivative of f of x, is equal to the slope of the tangent line to the graph at the point x, f of x. So this is always a slope no matter what geometrically. And that means if we want to use the derivative by finding it's dealing with its geometric nature, we can definitely do that for this one, but we need a graph. So our function is f of x equals 12. It's kind of an interesting function. No matter what value you have for x, it's constantly 12, no matter what. So we call this a constant function. That's weird. There's some little lag on this actually producing. Maybe I shouldn't use that for running out notes. Oh, there it finally goes in. So that's called a constant function. If we go to plot it, its graph would look like this. We go up a height 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh dear. Here we go, 11, 12. then the graph of that whole function looks like this. The height of the curve is 12, always, no matter what. So the second coordinate is f of x, which is 12. So that's our graph right there. But what we want is this new object. It says find the derivative. We call that f prime of x if we're using Newton's prime notation. And my axes look a little funny. Let me label that as the x-axis, just so it looks more sense where the actual x-axis is on this thing. Now coming back here, well, the derivative of f at x, whatever x you pick, is going to be equal to the slope of the tangent line anywhere out here. But notice, if you put a tangent line on this thing, the tangent line, here's some dots, hard to see, overlaps with the line itself. Any volunteers for what the slope should be then of that tangent line? I agree with Dana. The slope of that tangent line is exactly 0. And it didn't matter where x is. A horizontal line like this has always slope 0 at every single point on it. So move x to the left, maybe out here. Your tangent line, again, is horizontal. It's completely intersecting the blue line. So it would always, no matter what, have slope 0. So let's put here, the slope is 0. But now we connect the dots. The derivative is equal to the slope. And so we just say the derivative itself is always 0. This is really going to turn into one of our very first formulas in the next section, 3.3. Whenever we have a function like this, if we know it's a constant function, then the derivative is automatically 0 each and every time. We could use this definition of the derivative above to show it. But for example 3, we're just relying on the geometry here and our intuitive understanding of what the derivative is. So just to put down final thoughts on this one, the derivative of a constant is always 0. Always is a strong word, so it's nice to have something that is never going to break a pattern. The thing to watch out for is the constants could be weird. It could be square root of 2. It could have been pi. It could have been natural log 5. All of those would be constants, and the derivatives would always be 0. Well, any questions, folks, with that first one? Okay, so, well, we could use the geometric nature for the derivative for this function because it's, well, in all honesty, kind of a boring function. It's just this horizontal line. The only thing that could ever change here is how high the line is. To make it even more interesting, we can make this line have some kind of slant. And that's what's going on in part B right here. So we have a new function, g of x equals 7/3 x minus 9. Like before, what we want is the derivative. So we begin by saying g prime of x. I haven't drawn the graph yet on this, but anyone see what the derivative should be just by visual inspection? If we're not too sure, no worries. I mean, they're just our second problem along these lines. First thing we'd want to do is graph it. Oh, but I just got 2 chats to come through. We have Dana and Jamie saying 7/3. Good call, folks. That's absolutely what this would be. Why 7/3? Well, this function is in slope intercept form, so automatically the slope of every point of that tangent line must be 7/3. So that problem's done, but let's park here just for a little bit longer and actually plot the function just to get more intuition on what's going on with this one. If we were to plot this, we'd have to go down 9 units. So 1, 2, 3, 4, 5, 6, 7, 8. I never make these long enough. 9. So there's the y-intercept. Then we go up 7. 1, 2, 3, 4, 5, 6, 7. Right 3. And we'd be right here for our second point. Here's the, oh, that's kind of a weird angle that went off too. Let me try to fix that. So here's the graph of that line, if I can make that look a little bit more believable. This is y equals g of x. But now, if we're using the geometric nature of the derivative, what we do is we pick an x anywhere in the domain of the function. It would go up, hit a point here. And now for drawing a tangent line, right at a point where the function is linear, it's like the last example. The tangent line is equal to the same slope as the original function, so m is 7/3. But then once we found the slope, that's the value of the derivative at any x we would have picked, always 7/3. So that's kind of cool in a way. If we, again, use the limit definition of the derivative, we'd have arrived at the same value. But using the geometric nature, it tells us we don't have to do that for certain functions. Those are the linear ones or the constant functions. Let's add just a quick note to this one. This function is linear since the degree is 1. When it gets a little bit more complicated is when the degree gets higher and higher. If there's an actual curvature to this line, then it's not so straightforward to use the geometry of finding the actual value of the derivative without resorting to the full limit definition. So that's why, for example, if we have something that looks like, say, oh, sorry, that's the wrong notes. That's why if we have something that looks like this in the prior notes, oh, that's the same one we're looking at. I was trying to get to section 3.1. They're so similar. I think that's why it's confusing me. But this is the picture we were looking at in the prior section. If our curve has actual slope to it, so it's not linear, it's not constant, then, well, to find the slope of that tangent line is not trivial. We really have to run through that whole limit definition. But these are the nice cases where just knowing the type of function you're dealing with automatically gives you the derivative. Any questions at all, folks, with those two problems? Okay, let's try this out once more then. Here, on this last example of these notes, what we're doing is just practicing the definition of the derivative one more time. And watch out for this problem as well. When it comes up as an exam problem, it is a tricky problem, so let's put a quick note here. On exams and quizzes, say quiz 3 that we have coming out today, we must use the limit definition for full credit. And there won't be a lot of problems like these on the exams. Pretty soon in section 3.3, we'll see how to do all these a little bit faster. This is more just testing on the concept of knowing the original definition of the derivative and knowing how to complete that limit there. So it's a tricky problem. We'll practice it right away with that function. Any questions at all then before we launch into this one? Okay, first step as always, I would probably always want to write this out. The derivative of f, we're saying at x this time. In the prior notes, we said derivative of f at a, but that's just a different choice of a variable. We're really studying the exact same concept. This time we're using x to just emphasize from this old function, we're producing a new function with the variable x. This function is going to specify the slope of the tangent line at any value x we throw in. Through the definition of the derivative, we have to write out limit h goes to 0. This might be a good one for color coding. So let's go f at x plus h minus f of x, all of which is divided by h. So that's our limit to work out. First, we have to survive the function notation. So f of x plus h is going to do this. X plus h goes here and here where it's highlighted in blue. Let's work that out on the margin. F at x plus h is now equal to 3 times x plus h, power 2, minus 5 times x plus h, plus 1. So now we need to expand all these things out. This is going to turn into 3 times x plus h squared. If we like, we can write out like this to visualize it better. Then minus 5x minus 5h plus 1. Then it goes for a little bit here before we can finally get it all finalized. First thing I'd want to do is take 3, multiply by the group that you get after foiling this all out. So we'll get x squared. You get x times h 2 times, so that's plus 2xh. Finally, plus h squared. Now it's copying minus 5x minus 5h plus 1. Last things we have to do is distribute the 3 through and see if there's any like terms to combine. Doesn't actually look like it on this one, so this is what we get altogether. 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 1. So that's the result of f at x plus h, kind of the worst part of the problem. But this part in green is not so bad. Really, the only danger with the f of x is we have to recall to distribute the negative across all the terms in the group. So with that out of the way, we're going to start putting everything back together in the limit we have here by the red dot. Any questions first with the bit of algebra here on the right? Okay, looks like we're on our way with this one then. Next step, we can say this is equal to the limit as h goes to 0. Really long fraction part looks like. Let me put it just a fast border here just to make this more readable. So first in blue, we substitute in our result f at x plus h, which is this whole line right here, a lot of terms. 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 1. And slightly longer fraction bar. Minus goes in here. And then for f of x, let's put in a parenthesis just to remind ourselves to distribute. And then we're plugging in that original function, 3x squared minus 5x plus 1. That almost made it. Let me fix the border here. It's kind of funny, but with things overlapping like this, it makes it almost invisible to me to know where the fraction ends. So sorry about that. I probably should have moved that over further to the right. Does that look right to folks so far, however, with the format? Okay, next step then is the fun step. We're going to distribute the negative through that group, and that's going to give us loads of terms that are going to cancel. And the hint on this is every term without an h must cancel off some way, somehow. So let's carefully write it in. For me, the biggest mistake I make is there's so many terms, I just sometimes don't copy everything down. I might miss something. So copy everything down really methodically, and that protects a lot for that kind of error. So limit as h goes to 0. I'll drop the color coding at this step and write 3x squared plus 6xh plus 3h squared minus 5x minus 5h plus 1. A little bit longer on that. Here, distribute the negative through to get minus 3x squared, positive 5x, minus 1. All we're doing is flipping all signs of everything in green in that parenthesis. We're dividing everything by h, and now we're ready for some cancellations. So first, positive 3x squared and negative 3x squared add up to 0. What else do we have? 6xh. I think that's the only term there. There's only one h squared term, so no cancellations. Here we have negative 5x, positive 5x. Nothing combines with that one, negative 5h, but positive 1, negative 1 will cancel. So this is the survivors, 1, 2, 3 different terms in the numerator. I'll take the strategy of factoring h out of there, but that's an optional way to do it. If you cancel h right at this step, just make sure you cancel it here, here, and here from all terms in the numerator. Alternatively, factoring looks like this. Limit as h goes to 0 of h is factored out, leaving from here 6x plus From over here, it just drops a power by 1, so 3h. From here, it's just going to be minus 5. All of this stuff is still divided by h. And this is the massive cancellation we wanted all along. With those h's canceled, direct substitution says we can put h equals 0 right in for that h there. So now we get 6x plus 3 times 0 for h, yellow just to show the direct substitution, minus 5. So finally, our answer to this is 6x minus 5. And that's our value of our derivative from up here. Well, we did it, folks. We're not going for a tangent line. We just want to know what is f prime of x. It gives us that linear function, and that function right there is going to describe the slope of the tangent line to the original degree 2 polynomial at any value of x. It takes a lot of work to do these kinds of derivatives, and you might have noticed sometimes when this is a fraction, like in the section 3.1 notes, the algebra is pretty extreme. But if this was an exam question, I'm not going to go for tons of crazy algebra. It's going to be more contained like this one you see here. Well, any questions at all, folks, with that full rundown of using the definition of the derivative? Okay, well, let's save up these notes. And now we're going to move over to section 3.3, where we're going to start to look at different formulas for calculating the derivatives much faster. So let me close this first. We can probably close that. I don't think we need it at the moment. So now we're on section 3.3, basic differentiation formulas. Oh, I forget. I have a participant window on the right, which kind of hides my files over here. Okay, so here's how the note starts out. We have different formulas that we're going to take a look at, derivative of a constant and the power rule being the first two. And for each one of these, I want to show just a couple examples to demonstrate how they all go. Notice on this one, though, we're using Leibniz notation to describe each one of these derivatives. If we were to describe it differently, say in Newton's prime notation, we might have written it this way. If y equals c, where c is a constant, then y prime equals 0. So we're expressing the same thing over here. The only difference is when you say d by dx, we're referring to the derivative with respect to the x variable of a constant is 0. Over here, we're saying if y is a constant, then the derivative of y equals 0 as well. So this is pretty fast notation, but a lot of our formulas in our book are written in Leibniz notation, d by dx. So just to convey that thought, since this notation is brand new, d by dx is the same thing as saying y prime. We're talking about the derivative in either case. So just for a really quick example, let's say if y equals natural logarithm of 2, that's a pretty weird function to have here, but it is a constant function. We can plot it just to emphasize what it would look like. Y equals natural log 2. There it is. The height of this function at any point of x is natural log 2, 0.69315 and some change. So no matter where you go, you get that value. The slope of the tangent line at any point is always 0. And so it makes sense. Derivative must be 0. So if y is natural log 2, we can say dy dx is 0. Or we could have just said y prime is 0. Again, this is Newton's prime notation, and this is just our Leibniz notation. Well, that's how this problem goes. Honestly, this can be a pretty confusing differentiation formula because we have to know exactly what we mean by a constant. And that's what this was here, a constant as well. Any questions with our first formula of the day? I said first formula of the day, but more first formula of the notes. Okay, well, up next we have the power rule. But before we do the power rule, let's maybe do one additional thing. How would we know that this is always true, that the derivative of a constant is always zero? We would have to actually use the definition of the derivative. We won't do this on every single rule that we see here, but just to connect the dots from section 3.2 to section 3.3, this is what the work would really look like. So let's sketch this out. If f of x, now we're using function notation, equals c, where c is a constant, then if we didn't have this formula here, we would have to find f prime of x this way. Let me fix that. Writing this out is definitely not a good idea. This looks like we're saying f power 1 of x when we really want to say f prime of x. So I'm going to try to always avoid doing anything ambiguous like that. If it goes off at an angle, then that's the prime symbol, and you're really talking about a derivative. So this goes limit as h goes to 0, f at x plus h, minus f of x, all of which is divided by h. So now that's our tried and true definition of the derivative. If we start putting in things for f of x plus h and f of x, this is what we'll get. It's the limit as h goes to 0 of, now in the numerator, f at x plus h. Well, if f of x is equal to c, that means f at x plus h is also equal to c. In other words, the function is constant, meaning no matter what you put in here, the output is always c. Then from here, f of x, that's just a direct substitution. We go minus c, all of which is divided by h. But now the numerator is just 0 altogether. 0 divided by h is still 0. H just vanishes. This is the limit as h goes to 0 of the function 0 now. This just turns into the limit of a constant. Back in our limit laws, the limit of a constant is always that constant. And so we get 0 out. So the left-hand side, d by dx of c, we could visualize by f prime of x, when f of x is c. The output of 0 is what we got to right here. So no matter how we look at it, whether we're looking at, say, a graph where there's a horizontal tangent lying on the constant function, or if we do in fact use the definition of the derivative, we always get a value of 0 on this. Well, any questions at all, folks, with a second look at the formula here? Okay. Again, just to emphasize, we won't be using the definition of the derivative very much on these notes. This is probably the only exception to kind of convey what happened in 3.2 and what's going on in 3.3. The idea is every one of these differentiation formulas, like that one, for example, they're proved by using this limit definition of the derivative. Some of these proofs are actually pretty hard. So in the reading, if you skimmed through those, no harm done. So here's the power rule. And we want to make a pretty big deal out of this one. So let's emphasize here, the power rule is used a lot. So it's something that we absolutely need to get a really good handle on. It's a fast rule to apply. It says if you're taking the derivative of a power function, x to power n, what happens is the power that's n right here comes down as a coefficient, and then the new power goes down by 1. So let's write out a couple quick examples. If y equals, let's say, x cubed, then we can write out the derivative of y with respect to x would do this. Step 1, your exponent of 3 comes down in this way. So there it is. Step 2, write x to a power 1 less. By the red dot, the power was 3. So the new power 1 less would be power 2. And we did it, folks. That's doing a derivative extremely fast. If we were to do this one by the definition of the derivative, it is pretty tedious. I think that's a good 15-minute problem. So that's the power of a really nice formula like this. It's making computation massively quick based on what we did prior. Well, any questions, folks, with this example here of using the power rule? Okay, so at the moment, we have the derivative of a constant coming out to 0. That's our very important rule. We have a power rule that says differentiate x power n. You just get n times x to the power of 1 less n minus 1. But there's a lot more interesting functions we want to differentiate. For example, what if we had y equals 7x cubed? The power rule doesn't tell us how to differentiate that whatsoever because the power rule is talking about a coefficient of 1 in front of x power n. If we have a coefficient of 7, then this whole rule falls on its face. But here's where we can use the constant multiple rule. The constant multiple rule means you have a constant, that's the 7 in this problem, multiplying your function. So here, that's our constant. And the constant multiple rule, here's the constant c, multiplying a function f of x. So think of that f of x like x cubed, like we have in the example down below. The amazing thing about the constant multiple rule is the constant is unaffected. All you do is you take the constant multiplied by the derivative of f. So working that out, if y equals 7 to the power of x cubed, then we can say y prime or dy dx, your preference. I'm trying to mix up notations just so that we get good exposure to both, since they're both important. So same idea here. This is the derivative. What'll happen is 7's unaffected. So 7 goes here. We take x power 3 and differentiate that. So that's this step right here. 7 came out on the left. D by dx of f of x, if we use prime notation, would just be x cubed prime. We still have to work out this last derivative, but then this is the power rule. What happens is 7 copies over. Next, the power 3 by that red dot becomes a coefficient, so it's multiplying 7. New power of x is 1 less, so now power of 2. And simplifying, we get 21 x squared. So what the constant multiple rule enables us to do is expand from something like this, x cubed, to having more generic functions, 7x cubed or maybe negative 12x cubed. We can differentiate those just by using this process here. Any questions at all, folks, on running through this one?
I have a question.
Yeah.
So is this similar to the power rule, but you're just instead of multiplying by the coefficient 1, you're multiplying by...
Yeah, absolutely. That's a great way to say it too. There really is a coefficient 1 here from the very get-go, so that would have been a 3 times 1, like you're saying. All we're doing is expanding and saying it could work with any coefficient you could put in there. Does that make sense with your question so far?
Yes, it does. Thank you.
You bet. And thanks for mentioning that. I think that's a great way to think about how these rules are really interacting. This is really just a general power rule in that kind of sense. Other questions at the moment? Okay. Well, notice even with this problem right here, we still have a pretty big limitation. Suppose, for example, you wanted to differentiate maybe this function, the one on the very bottom of the notes. Let's say not using the definition of the derivative, so I'll just scroll to that part. If we want to differentiate that thing, well, we could do the 3x squared derivative, but now there's a whole bunch of other terms, the minus 5x and plus 1. Nothing so far in our notes tells us how to deal with more than one term. So that's where we go down to these new rules. The sum rule and the difference rule. They say if you're differentiating two functions added together, maybe they're stuff like, say, 7x plus 5, then you just differentiate going term by term. You take the derivative of the first term, add to it the derivative of the second term. So really all this is saying is, in a real sense, the differentiation operator distributes across addition. Likewise, it distributes across subtraction. So it's kind of nice to have that kind of algebraic formula. And finally, that allows us to take something like this. For our new example, let's actually take the one that we did painstakingly with the definition of the derivative. Let me remind myself what it was. It was 3x squared minus 5x plus 1. Now, these formulas are stated with two functions, but they can be expanded for three functions, or excuse me, two terms is what I meant to say, or two functions. It could be dealt with three different functions or more. So if you have maybe 3 terms, 5 terms, you're just using these over and over again. So differentiate that, and you'll get dy dx equals, first we differentiate 3x squared. 3 stays where it is by the constant multiple rule, multiply by power 2 on x. And the new power of x is a power of 1. But x power 1 equals x, so we would just generally leave it like that in its more simplified form. Then we do it again over here. When we differentiate this one, it is a power rule once again, but you know it's a little bit harder to visualize. So let's take this right here and just make it its own problem. If y was equal to negative 5x, we need the constant multiple rule and the power rule, just like differentiating 3x squared. But what's the power on x? Well, if it's just x, this time for the purpose of visualizing it, you might want to put in the 1. Now, here's what y prime would look like for that. Constant multiple rule says negative 5 stays exactly where it's at. It's multiplied by the exponent. That's an exponent of 1. But now the new power of x, no matter what the old power was by the red dot, always goes down by 1. So the new power of x is 0. But anyone recall what x power 0 ought to be by laws of exponents? Absolutely, Jamie. This one comes out as a 1. So we can say here, since x power 0 is 1, we have that y prime equals just negative 5. And that's where this would become right here. So that's one way to think about this one. You can think in terms of it's just really the power rule. If the degree is 1, so you see an x is just gone, and you pick up a negative 5. But there's another way to think about this. So if you're thinking in your mind's eye, we've done this one before. You're absolutely right. Let me pull this up real quick. Another way to think about the derivative circled here is that it's really just doing this. Oh, that was one we did on the notes here. Hang on, let me pull that out. I shouldn't have closed section 3.2. We need it right here. Let me get this scroll to the right spot, and I'll start over that thought that I was trying to connect. Here we go. I was thinking in terms of this function right here. So let me restart my thought on this. With the one that's highlighted in purple, you can use the power rule like we just did over here on the margin. But you could also say, well, negative 5x is no different than that. It's a linear function. It's negative 5x without an intercept, or intercept of 0 is better to say. So the derivative of this has to be the slope. The slope of that kind of linear function is negative 5, just like the slope of this one was 7/3. So that's kind of a cool function in a way. You can think purely geometrically, or you can just use the power rule. In any case, the derivative of that is nothing but negative 5. So we go minus 5. Then we go to differentiate this right here. What would the derivative of 1 be? Any volunteers for that derivative? Good call, Alejandra. That one has to be 0. That's because this is just a constant. So notice back in the notes here in 3.2, when we had a constant function, the 1 and 12, that's no different than this one, the positive one. The derivative is 0 no matter what you do to that thing. So we'll go plus 0. Honestly, you really don't have to go plus 0. We're doing it this time in the notes because we haven't taken a lot of these derivatives, and we're just being extra careful. So what the sum rule, difference rule does is it interacts with every rule that's above there in the notes, the constant rule, the power rule, the constant multiple rule. So now we can say derivative of that goes over here and becomes 6x minus 5. And that's the result we got, but it took a lot of work to do this by the definition of the derivative. These were the steps we had to take. So I think most people would say that's not the best way to do these kinds of things. The reason we do it once is it's just a reminder that in calculus, everything that's interesting is essentially defined by a limit. So we won't do a lot of these problems. There's one on the quiz. We'll have one on exam 2 and potentially one on the final exam. Aside from those, we're always doing the derivatives in this way. And you can tell if it's going to be something requiring a limit because I'll always put in the instructions, calculate the derivative by using the definition. That means we're doing that kind of limit. But, when you're doing a quiz or exam problem, you kind of know the answer if you use differentiation formulas. So even if you made a mistake on the limit here, you'll know right away because the derivative by our formulas here is really fast to find. Well, any questions at all, folks, with visualizing these derivatives here? Okay, I have one more differentiation formula on the notes, and this one is the world's best all-time derivative. It's called the derivative of the natural exponential function. What makes it natural, as the author calls it, is the base is e, which is approximately 2.71. That number turns out to be extremely special. In fact, it even has a name. E is called Euler's number, which is Euler is a mathematician spelled E-U-I-E-L-I-E-R number. Euler's number is special because when you differentiate this function, e to the power of x, the derivative of it is itself. And that is really kind of wild in a way. So just for a really quick example, if we had y equals, let's say, 5e power of x plus 3x to the power of, let's make it be, how about 1.1? Here's how the derivative in this case would go. We would write down below y prime, or dy dx if you prefer, equals, first, that 5 is multiplying e to the power of x, so we're using the constant multiple rule. 5 is unaffected. We take the derivative of e to the x, but that is itself by the rule that's expressed up here. So we just get 5 times e to the x. And that's really nice, where all we're doing here is just copying. Here it gets a little bit more tricky. We'll go plus 3 multiplied by the old exponent, 1.1. New power of x is 1 less, so take 1.1 minus 1 to get a new exponent of 0.1. That looks pretty weird, but this could be anything. It could be pi. If that exponent was pi, pi would go right here, so now it's 3 times pi. And the new exponent would be pi minus 1. Kind of awkward to write in, but that pattern for the power rule always goes exactly the same way. Then simplifying, we just get 5e to the x plus 3.3 multiplying those constants, x to the power of 0.1. So that's our last row of these notes. Any questions, folks, with our example to go along with this one? Okay, I did have one comment I wanted to make about this. The reason I put down an example with an exponential function, that one's exponential, and a power function, x to the power of 1.1 is referred to as a power function, is because these have completely different rules for differentiating. The derivative of e to the x does not take the x down as a coefficient, and we do not put x minus 1. However, if it's a power function, then you absolutely do that pattern. 1.1 came down, and we subtracted 1. So how can you tell you have an exponential function? What makes it exponential is x is in the exponent position. When that happens, the derivative is highly non-standard. It became just itself. We can't use the power rule whatsoever. And now what makes this a power function is the fact that x is a base. When x is a base, here, we can use the power rule. So this is a really tricky example, in my opinion, especially when it's kind of out in the wild. Think of this as coming up as a random quiz problem or random exam problem. You would have to absolutely recognize that as an exponential. So the derivative didn't change, 5e to the x. And we would have to recognize that as a power function to get the work to come out right. So that's why we're spending time just looking at the formulas instead of ripping through them and scrolling down. These are good ones to see with examples. And if you ever feel like you need a good refresher, take another look at these lists and it'll help you out quite a lot. Any questions or comments whatsoever to this stage? Okay, we're making some pretty good headway here. So on my next examples, we're going to start redoing some of the material that we did in the prior section. In section 3.1, we want to find the equation of a tangent line to a curve at a point. This problem is at 1, 2. And to make that work, well, we used the limit as h goes to 0 of f of x plus h minus f of x divided by h, putting in a 1 for the x. But in this section, we're redoing how we approach this problem. So let's redefine how this ought to go, because we really want to use the basic differentiation formulas. We're not using the limit definition for the derivative. So here's our step 1. Very first thing we want to do is take this and differentiate it with respect to x. So either call it y prime. On these notes, we'll call it dy dx. Then we just start using our different differentiation formulas. By the red dot there, we use the power rule. That will turn into 2x. On this one, negative 5x, if we differentiate that, we just get a negative 5. And the derivative of 6 would go to 0. And so the whole thing is just a 2x minus 5 altogether. So that completes our step 1. Any questions, folks, on finding that derivative here? Okay, I think the notes are more readable if we actually just call it step 1. I'll go with that route. Now, step 2. The notation on this looks a little bit weird at first. So part of the reason for using Leibniz notation is just to show what that notation is really trying to say. In step 2, we're coming up with the slope m. To find m, we have to use the derivative over here by the red dot. That derivative specifies the slope at any value of x. Well, we don't want it at any value of x. We want it for specifically x equals 1. So we're plugging 1 right inside there instead of the derivative. That will give us the slope of the tangent line at the original point, 1, 2. But here's how we write this out. This turns into m equals. We take our derivative, dy dx. This notation is clunky, but it's also really common. That's why we're studying it here, just so that when it comes up again later on, we'll be familiar with what's being asked. Next thing we do is put a bar that goes like this. This is an evaluation bar. It means we're plugging in a number for x, and we write it this way. So altogether, this whole notation is saying the derivative of y, that's the numerator part, derivative of y, with respect to x, so that's the denominator part, evaluated at x equals 1. That's the vertical bar with x equals 1. That is a pretty heavy, crazy notation, but unfortunately, it's common enough that we have to be careful with it and really study it, see what it's saying. In the end of the day, this clunky notation is just saying, take that 1, plug it in right here where we had our dy dx. So it turns into 2 times 1 minus 5 And that means the slope of the tangent line is automatically -3. And this is another one of those problems we did in section 3.1. That was our first example, I believe. That's a tough problem when you're using the definition of the derivative. But going forward, if you're finding the equation of the tangent line, it's always going to be this way. Just use differentiation formulas to run through it. Any questions, folks, with step 2? Okay, step 3 is us just finalizing and finding the actual equation. So here's how it goes. Step 3, we now have a slope, m, equals -3. We take the original point, which is 1, 2, write x1, y1 equals 1, 2. And then, just like we did earlier in the notes, pick your favorite equation to build your line. I'll use the point slope form, which goes y minus y1 equals the slope m, multiplying x minus x1. So the y1 is provided as the 2. X1 is provided as 1, the original point they gave us. So now substituting in that information, we are going to get y minus 2 equals the slope m, which was a -3, multiplying x minus 1. So 3 substitutions in, we have an equation for the line. Traditionally, we always want to solve this for y to get the point slope form. So this will turn into y minus 2 equals -3x plus 3. Add 2 to both sides, and we finally get y equals -3x plus 5. So that's our conclusion. This is what we wanted, the slope of the tangent line. Excuse me, the equation of the tangent line at 1, 2. That deserves an exclamation mark because last time we did this problem, I think I took at least 10 minutes to run through the full process. Notice the slope of this tangent line is the -3. Just as a check on our algebra, it better be -3 since that's what we specified on step 2, that same slope. Well, any last questions, folks, on getting through this one? Okay, maybe one last additional thought. How would you check this out? Well, we've done it before, but imagine this is a quiz problem and you just wanted to be sure you had the right answer. Here's what I suggest you do. Use any graphing calculator. Desmos is just convenient for me to use in class. Plug in your original function, y equals x squared minus 5x plus 6. So we have a nice degree 2 polynomial there. Then after that, on the second line, plug in your tangent line equation, y equals -3x plus 5. Go to the point 1, 2, where the tangent lines should intersect. Let's see, there it is, 1, 2, looks like a real point of intersection. And you should see this feature happening right at 1, 2. Zoom in on that a whole lot, and the tangent line in green and the polynomial in blue should become more and more the same. So let's zoom in. At this stage, I would say this is really great numerical evidence. We have done everything perfectly. We have that both the tangent line equation and the graph of the polynomial, if we zoom in even further, they are now just totally indistinguishable. Well, that means we have a great tangent line. And if it wasn't -3, it was say -2.999, that's pretty close, but here everything looks pretty off. So this is extremely numerically sensitive. And if you have the exact right answer, you would never see this picture here. Well, that's our run through of how tangent lines go. What we're going to take a look at next is higher order derivatives. But any questions whatsoever with this problem here? Okay, So by higher order derivatives, what we mean is, sure, you could take something like dy dx or call it y prime or f prime at x, but occasionally we want to differentiate the derivative. That's what's going on in example 2, where it says, calculate f triple prime at -1. Well, that means we're going to take f of x. We start by differentiating it once and writing this out. F prime of x. It's a function of x in its own right. Looks like we're going to use a power rule several times here. Let's zoom in a bit to really visualize it. Starting with x power 4, this just turns into 4x cubed. The mantra is the old power 4 is now the exponent, and the new exponent is 1 less, so a power of 3. Any volunteers for what the derivative of the next term should be? Jamie says 12x squared. Absolutely. With a negative sign, we'd get negative 12x squared, but you've got the exact value there. So altogether, negative 12x squared. Good call. So it's just the power rule and constant multiple rule in action. 3 multiplies the negative 4 to get the 12. The new power is 2. Then just keep on going. Next term over, derivative of 19x squared. Well, that'll be 19 times 2, so 38. Power of x is 1, so we'll just write it in as a x. Power rule works here again, but the power of x is a 1, so it's 3 times 1 for 3. New power of x is power 0, but x power 0 is a 1, so this just turns into a 3. And you can also visualize this by thinking once again, that's a linear function with slope 3. The power of x is 1, x vanishes, and you just get the slope. Lastly, root of negative 18 is a constant, so that just goes to 0 upon differentiating. So it's going to be plus 0 right here. You don't always have to write in the plus 0. Again, this is just to emphasize in the notes why that term is gone. So we did the first order derivative, f prime, but we want to take the third derivative, f triple prime. So what we do next is we go to this function here, and we just continue on. F double prime is visualized that way. So this is the second derivative. Let's write that out. The second derivative is visualized by just putting 2 prime symbols on it. But the way it works is we just imagine this is the new function we're differentiating and just do as before. 3 comes down multiplying the 4, so it's 12. Now x to the power of 2. Here, 2 multiplies the negative 12, so it's minus 24. X to the power of 1, so we'll just write in an x. Over here, 38x, that gives us just a 38. And the plus 3 goes to 0. Here, this is how we would typically write this all out. I'll leave off the plus 0 since we know it's a constant and just vanishing. Well, does that make sense to folks at the moment? How to get to the second derivative? Okay, well, that was so fun. We'll just do it again. We're trying to get to f triple prime of -1, but the first thing we have to do is say, what is the third derivative? So differentiate that again, and we'll get f triple prime now equals, up here, the power of 2 multiplies as before. So now it's 24x to power 1. Derivative of the linear function just gives us the negative 24. And at that stage, our work is done. So this one is the third derivative. And we'll do some applications later on these notes where we do really use these higher order derivatives. For example, if this was describing the speed of a moving object, think you're driving a car, then the first derivative would be the velocity, what you see when you look at the readout of your speedometer. The second derivative is going to be your acceleration. And the third derivative, well, that's the rate of change of acceleration. Sometimes that's called a jerk function. And it's just describing the rate at which your acceleration itself is changing on the third order derivative. So that's the kind of physical intuition you can think about when you're doing these higher order derivatives. But finally, we're getting to the last part of this problem. We want to evaluate third derivative at -1. So we'll say, therefore, f triple prime at -1 equals, just go to this derivative, plug in a -1, we'll get 24 times -1 minus 24. But that's just -24 minus 24 for a -48 altogether. So the takeaway on example 2 is we're just practicing differentiating these functions more and more, but you can always take higher and higher order derivatives. And if you're asked to do evaluation, just plug in the number where you have your x. Oh, that's a great question. Thanks for asking that, Jamie. The triple dots that I put right here is just a quick way to say therefore. Oftentimes I use that whenever we're connecting, say, a lot of different algebras, all going in to one conclusion that f triple prime is -48. So that's just a way to say, therefore, by the work above, that's our answer. Other questions so far?
So you break that whole thing down and then plug the -1 in.
Exactly. We go break down to the third derivative, plug -1 into that location.
Okay.
So essentially it looks like this with a little bit extra color coding.
Okay, thank you.
Yep, absolutely. Other questions at the moment? Okay, well, we've done a lot of work on these notes so far. Let me show you where we're going with these notes. This is an interesting problem in its own sake. It's purely just a math problem, zero context whatsoever. So the next problem we're going to be taking a look at a real honest application. We're modeling the length of Alaskan rockfish. We need to calculate a derivative. This one's indicated in Leibniz notation. And the hard part about it is giving a practical interpretation. We definitely want to go very carefully through a problem like this one. And I wrote example 3 is a common question for exam 2 and the final exam. So we'll see these kind of questions more and more. But the real meat of the notes are these down below. On example 4, we're just going to differentiate a lot of different looking functions. And these will be pretty similar to what the actual homework problems look like in WebAssign. I have quite a lot here, but that's because we just want to get a lot of additional practice for these brand new tools of finding derivatives. But I think for where we're at right now, I think this will be a pretty good stopping point for us. There's a lot to absorb in this material right here. And I want to take my time going through this kind of question because it is pretty tricky on interpreting a derivative. Also, I have an interruption with my office hours and a meeting to get ready for pretty soon. So we're ending class just a little bit earlier than normal. But any questions at all, folks, then, before we call it a day? Okay, well, when we come back next Monday, week 7, we'll take a new look at these kinds of things, running through power rule, the constant multiple rule, and so on, and practice more and more derivatives. Probably at the end of the day on Monday, we'll be in the next section 3.4, but that's for sure something we'll hit really hard next Monday as well. Well, this will be a good stopping point for us today then, folks. And again, sorry about the office hours interruption. If you have questions that you'd like to talk about from homework or quiz, don't hesitate to send me an email. I'll be happy to help out. And my office hours are back to normal on tomorrow, Thursday. But have a great weekend, folks. If I don't hear from you, then I already said have a great weekend, but have a great weekend in either case. Yep, you bet.